Hello everybody, welcome into another lesson. So today we are going to talk about rotations. So when you rotate something, of course, you're just moving the angle of it. You're definitely not changing the size. You're simply just rotating it, you're moving it. If I rotate this board around, I could spin it around, it would just be at a different angle, but I certainly haven't changed the size. So a rotation itself is an isometry because it does not change the size. Now, rotations in general, they can go one of two ways. They can be the normal positive angle, which would be counterclockwise. So if I start from the origin and work my way counterclockwise like you would normally picture an angle, that's a positive rotation. In a minute we'll talk about negative angles, which indicate clockwise rotation. And it's not that there's really such a thing as negative angles. Their angles are only called negative because it indicates what direction they're going. I mean, there's no real such thing as a negative angle. Just if you see a negative angle, that means it's going clockwise instead of the normal counterclockwise. So let's talk about this here. So I have, of course, the vertex of the angle at the origin, point O, which goes to a point P. Well, I want to do a transformation here by rotation. This notation here, that cursive R, so if you see a cursive capital R, that means a rotation. It's not like the normal regular uppercase R you would see, which means reflection. If you see the cursive R, that means a rotation as opposed to a reflection. So that's how they're denoted. That's how they're separated. So what this is saying here, this is a rotation through the point O at the origin of 45 degrees at the point P. So if I rotate through the origin at point P 45 degrees, positive 45 degrees, it'll give me the transformation of P prime. So P would have shifted to P prime if I rotate this 45 degrees. Now, there's other ways I can rotate also. Let's do another demonstration here. Let's say this time I put P prime here. I would have to rotate 90 degrees, right? If I rotate 90 degrees, that'll put me from the x-axis to the y-axis. And this would be a rotation through the origin 90 degrees at point P, would put me at P prime. And here's my 90 degree rotation from through the origin at point P would put me at P prime. So that's a 90 degree rotation. Now, let's do another rotation here. I'm just going to demonstrate this very thoroughly. Let me reconnect my axis. Alright. Now, if I do a rotation through point O at point P, or at point O through point P, I get P prime. This time I'm going to rotate it 135 degrees. That's what that means. So, if I rotate 135 degrees, I'll get from P to P prime. So I've just rotated this 135 degrees. As you imagine, you can rotate it other ways too. Now, let's talk about 180. There is something special about 180. There is definitely something special about 180. There's actually a whole thing just devoted to 180-degree turns. So, if I want to, let's see, I'm going to put P prime on this side, and as you can see, that would be a 180-degree rotation. So, if I rotate through point O at point P 180 degrees, I'll end up at P prime. Now, 180 degrees is also called a half turn through O. It's the same thing as saying a half turn through point O at point P, which would give you P prime. You think of a half turn, that's 180 degrees because a whole turn is a full circle. If it comes back full circle, you're back to where you started. So if I do a half turn through O at point P, I will be at P prime. So a rotation of 180 degrees can also be labeled as a half turn. This means half turn through point O at point P equals P prime. So that's a notation for the 180 degrees. Now this is where you're going to see angles could be greater than 180. Because when you deal with a circle, you go up to 360 degrees. So yes, you actually can get angle values greater than 180 degrees. Let's demonstrate here. What if I wanted to go 225 degrees? So here's my P prime. This time it's going to be the rotation through point O at point P 225 degrees. So a rotation through point O of 225 degrees at point P equals P prime. So I've started here, I've gone all the way down to here. I've gone 225 degrees. So far I'm still going counterclockwise. We'll get to clockwise in a minute. Now, let's see here. This time I'm going to put my P prime down here on the negative y-axis. This would be a rotation of 270 degrees. So if I rotate through point O 270 degrees at point P, that gives me P prime. That's going to put me all the way down here on the negative y-axis. That's a 270 degree rotation, which would be 3/4 of a circle. Let's see. Let me just reconstruct this. Now this time, let's go 315 degrees. So let's say I rotate through point O 315 degrees at point P. that's going to look like this. I start here on the positive x-axis, go all the way down to here. So that is a 315-degree rotation, since I'm still going counterclockwise. That would be a rotation through point O of 315 degrees at point P would go to P prime. So P would have shifted all the way to P prime by rotating at 315 degrees. And then, of course, all that's left is, you guessed it, the 360-degree rotation. So let's say I rotate through point O at point P 360 degrees. That'll give me P prime. So I start here. I'm going to rotate all the way back around. What do you know? I'm back where I started from if I go 360 degrees. Which means P and P prime are actually at the same coordinate, because I've literally gone all the way back to where I was if I rotate 360 degrees. It's come full circle. Now a full turn can be denoted as F sub O through point P would equal P prime, which actually would just equal point P. You would literally be back to where you started from. If you do a full turn, you get the point you started with. So your transformation and the point you started with itself are the exact same, since you just did a full turn. Alright, so those are positive angles. Let's talk about negative angles. Now, what I'm teaching today, these rotations, are very similar to the unit circle in Algebra 2 trig later in the course when we get into trigonometry. There's something called the unit circle for trigonometry, which works very similarly. Eerily similar, okay? Now, what if I want to rotate this negative 45 through point P to yield to P prime? Well, so this time I'm going to have a rotation through point O at point P of negative 45 degrees to get to P prime. So remember, a negative angle, you're going to go clockwise. If you picture how a clock goes, it goes this way. We were going counterclockwise, which went this way. Now for a negative angle, we're going to go clockwise. So I would put my P prime down here, and then here's my rotation of negative 45 degrees. My rotation of negative 45 degrees would look like this. So I started at P, rotated it 45 degrees clockwise, and got from P to P prime. Now, another interesting thing, there are other names for this. So let's say you don't like working with negative angles. That's completely fine. There is a positive angle equivalent to this. If you take your negative angle and add 360 to it, so what's negative 45 plus 360? Well, that's going to be 315. This would be the exact same as a rotation through the origin of 315 degrees at point P. That would also equal P prime. So you could rotate at 315 degrees counterclockwise and end up with the same result. Alright, so let's see here. I'll go, yeah, let's do just a couple more. So let's put P prime here. Let's say I rotate this negative 90 degrees. So I'm doing a rotation through point O at point P of negative 90 degrees would give me P prime. So a negative 90 degree rotation would look like this going clockwise. So I've gone negative 90 degrees, I've ended up from P to P prime. Which, if you don't like working with negative angles, just add 360 to 90. That's the exact same equivalent as a 270 degree rotation through point O, point P. You'll get the exact same thing. It would be the same as going 270 degrees counterclockwise. You'd end up at the same result. Let's do one more here. Let's say I put P prime right here. And then I go 180 degrees counterclock. If I go 180 degrees clockwise, I've gone from P to P prime. I just went 180 degrees clockwise, which would be a rotation of negative 180. So if I rotate through point O at point P negative 180 degrees, I end up at P prime. So I've rotated negative 180 degrees, which the equivalent to that would be a negative half turn through O at point P would equal P prime. So if I go 180 degrees in the negative direction, that's the same as a negative half turn. Which makes sense, right? That'd be a negative half turn. One more, I guess. Notice negative 180 and positive 180 would give you the exact same result because 180 is half of 360. So whether it's a negative half turn or a positive half turn, you'll end up in the exact same place. It just basically indicates which direction you're going. That's all it does. So let's say I rotate through point O at point P negative 360 degrees. Well, 360 degrees is still 360 degrees, but negative 360 would be clockwise all the way back around to where I started. So my P and P prime coordinate would be the exact same because I would end up exactly where I started even if I rotated negative 360. Now here's one for you. One more because I want to go greater than 360. Because in theory, circles can go on infinitely, right? Which we're going to learn about trig functions in Algebra 2 trig, which are actually infinite and periodic as opposed to finite. But let's say I rotate through the point O. At point P, I go 720 degrees. What if I rotated this 720 degrees? That's actually not that bad. I start here. I'm going to go counterclockwise since it's positive. So there's 360, which means I go again for another loop. If I come all the way back around again, I've gone 720 degrees, which means I'm doing two full turns. I just do two full turns and I'll still end up in the exact same place I was. So my P and P prime would be the exact same. I've just done 2 full turns, which would still give me P. I'd be back to where I started. And you can rotate negative 720 degrees, which would be clockwise, and you'd still end up back where you were. You just rotate twice. So that's the idea of rotations in general, and positive and negative angles. And again, there's truly no such thing as a negative angle. If you see a negative angle, it just means it's going clockwise as opposed to the normal counterclockwise. That's all that really means. And when we get into trigonometry and algebra 2 trig, you'll even see negative lengths, which again, there's no such thing as negative lengths, but you will see that just indicate what direction it's going. Okay, so let me set up an equilateral triangle here. I'm going to set up an equilateral triangle, or do my darnest to, because I can't draw to save my life. Alright, so we have equilateral triangle PST with the center of the equilateral triangle at point O. We are going to do some rotations, okay? So let me set these up for you here. We want to find the coordinate, the new points, if you do a rotation from point through point O at point P, through point O at point S, and through point O at point T. So let's find the rotation through point O 120 degrees at point P. Alright, so I'm at point O. Through point O at point P, I'm going to rotate this 120 degrees. Where am I going to end up? Alright, let's start with something. If you have a triangle, right? We know that there's always a circle circumscribed about any polygon in general, which means the sum of the exterior measures of any polygon is always 360. So suddenly that's starting to come back from earlier in the course when we were talking about triangles and polygons. The sum of the exterior angles of a polygon is always 360. And the idea that there's a circle circumscribed about that polygon. There's this continuous circle. Well, if there's 360 degrees around the triangle, this is an equilateral triangle. What does that mean? That each of the sides would be a 120 degree arc. You would do an arc of 120 here, 120 here, which would put you at 240, and another 120 here, which would put you at 360, all the way back around. So if I go through point O at point P 120 degrees, I'm rotating this in a positive direction, meaning I am going counterclockwise. If I rotate through point O at point P 120 degrees in the positive direction, where's that going to put me? That's going to put me at point T. That'll put me at the point T, because I've gone through point P, rotated this 120 degrees, that'll put me at point T. Alright. Now let's say I rotate through point O another 120 degrees, this time at point T. So now I am still at point O, rotating through that at point T another 120 degrees counterclockwise. Where will that put me? Well, that'll put me at point S. If I'm going 120 degrees counterclockwise, that'll put me at point S. And then if I do a rotation through point O another 120 degrees, this time at point S, where will that put me? So I am going through point O at point S. I'm going to rotate counterclockwise 120 degrees. That'll put me at point P. So it's just a matter, O tells you where the rotation starts. It's really at the point it is that you want to worry about. So if I go 120 degrees counterclockwise from P, I'll end up at T. If I go 120 degrees counterclockwise from T, I'll end up at S. If I go 120 degrees counterclockwise at S, I'll end up back at P. And you notice we did a full 360 degree rotation between the three of these. We came right back to where we started. So yeah, that's a positive rotation. Now, why don't we get into a negative rotation? So this time we're going to rotate through the point O at point P, but we are going to go counterclockwise because we're going to rotate at negative 120 degrees. So if we do a negative rotation, that means we're going clockwise. So if I go from point P 120 degrees clockwise, that will put me at point S, since that's a negative 120 degree rotation. Now let's say I go through point O, negative 120 degrees at point S. So this time I'm starting at S. If I rotate this negative 120 degrees, that means I'm going clockwise. I would end up at T if I go clockwise. And then of course, I'm going to rotate this through point O another negative 120 degrees. This time I'm going to rotate through point T. Which means, let's say I start at point T and I rotate this clockwise 120 degrees, so negative 120 degrees, I would end up at point P. So, and then you notice we've come back full circle again, albeit in the negative direction. All right. Now, this time, we're going to go through each of these points. We're going to rotate 240 degrees in the counterclockwise direction, in the normal positive direction you're used to. So if I go through point O at point P and I rotate this 240 degrees, well, think of your circle, right? Each of these arcs along P to S and then S to T and T to P is 120 degrees. So if I want to rotate 240 degrees, I got to go two of those arcs. So if I start at point P and go counterclockwise, I'm going to be at point T. That would be 120. If I go another 120 to be at 240, I would be at point S. So a 240 degree rotation would actually put me at point S. Now this time we will start at point S. We'll go rotate through O 240 degrees at point S. So again, if it's a positive angle of 240, I need to go counterclockwise. So if I go 120 degrees, that put me at point P. Go another 120 to put me at 240, I would be at point S. I'd be at point T. So that would be a point T for that rotation. And then this time, let's say I go through O 240 degrees, a rotation of that at point T. So I need to go again counterclockwise 240 degrees. So 120 would put me at S, another 120 would put me at P. So that's what a 240 degree rotation would look like. One more for this triangle. Then we'll do some others. Alright, these will actually be pretty easy. This time I'm going to start again at point O through point P. I'm going to rotate a full 360 degrees. Well, 360 degrees just takes you all the way back around to where you started, right? That'll put you right back to where you started. So if I rotate through point P, I'll be right back at point P. If I rotate 360 degrees from point O at point S, that'll put me right back at point S. Then if I go the full 360 degrees through point O at point T, I'm going to be back at point T. So 360 degrees is just an entirely full turn. You'll end up right back at where you started. Alright, so there's the triangle one. Now, let's do this. Make this as regular as I can. I did the best I could with it. Oh shoot, I'm really bad today. I can't draw to save my life. I've already told you guys. Tell you what, it's a good thing I'm not an art teacher, right? There we go. That's what I wanted. That's exactly what I wanted. All right. So, we have here a regular hexagon that is split into 6 equilateral triangles, which makes sense because the central angles of a hexagon, of course, would be 120. So you put, if you draw the diagonals, that splits them into half. You would have 60, and then each interior angle of a hexagon would also be another 120. You split them in half, you would get 60 with the diagonals. So you have 3 equilateral triangles, right? We are going to figure out 60-degree rotational increments. So let's say I rotate 60 degrees through point O at point E. So I'm going to go 60 degrees, right? Through point O at point E, I'm going to rotate this 60 degrees. Where would that put me? Think about it. This is split into 6 equilateral triangles. So if you take the 360 degrees, which would be the sum of the exterior angles around it, you split those into 6 separate equal pieces. That means each of these arcs is 60 degrees. So if I rotated 60 degrees in the counterclockwise direction, the normal positive direction from E, I would end up at F. That would put me right at F. If I rotated positive 60 degrees, I would be right at F. Okay. Now this one is a little bit different because it's going to ask you the same question, only you're going to go negative 60. So if I rotate through point O at point E negative 60 degrees, what does that mean? I'm going clockwise now. I'm going to go in the clockwise direction. So if I go 60 degrees clockwise from E, that'll put me at point D. So I'd end up at D if I rotated at negative 60 degrees. All right. Now, what if I rotated this through O at point F 120 degrees. I'm going to rotate this 120 degrees this time in the positive direction, so the counterclockwise direction. So 60 degrees would give me A, 120 degrees would put me at point B. So I would actually end up at point B if I rotated from F 120 degrees. That would put me at point B. Alright, so this time I'm going to rotate, of course, through O at point B, but negative 120 degrees. Let's rotate this negative 120 degrees, which means it's actually going to go clockwise. If I'm going clockwise, I'm going this way. So from B to A is negative 60, and then from A to F is another negative 60. So this would put me at point F if I rotated this negative 120 degrees. Alright, and then I got one more for this one. A little bit different though. So we have a whole half turn through O at point A. We're going to do a whole half turn through O at point A. What's a whole half turn? That's a 180 degree rotation in the positive direction, which would be the counterclockwise direction. So if I rotate this 180 degrees, which would be a whole half turn, A to B is 60, B to C would put you another 60, so there's 120. C to D is another 60, that puts you at 180 degrees. So if I did a whole half turn from point A, that would put me at point D. So these rotations truly aren't that bad. Now, I got one last set of exercises here, which I think you're going to like actually. They're kind of cool. Alright. Let's do this here. I'm going to set these up here. That means I might want to move this over a little bit. I'm just trying to draw you some real cool stuff here. Alright, so then that's going to put me... not the most accurate representation, but... Alright, so, as you see, we have 4 triangles here, which are all isometries. They're all the same lengths and all that. So, we're going to try to identify different transformations. You're going to have to determine, is it a reflection? Is it a whole? Is it a half turn? Is it a rotation? Is it a translation? Anything like that. So, let's go ahead here. What's the change from triangle 1 to triangle 2? So, if we were to get from triangle 1 to triangle 2, what would that be? Would it be a reflection? Would it be a translation? Would it be a rotation or a half turn? I think it's plain to see this would be a rotation. It would be a 90-degree rotation at that. So from triangle 1 to triangle 2, that is a rotation. So you actually have a rotation from triangle 1 to triangle 2. Alright. How about from this time we'll go from triangle 1 to triangle 3. So let's look at triangle 1 to triangle 3. Well, if you look from 1 to 3, that's a reflection, right? You just changed your x-coordinates. That would be like a reflection in the y-axis. So this one is actually a reflection. 1 to 3 is purely a reflection. Alright. So let's go from triangle 1 to triangle 4. Let's look from triangle 1 to triangle 4. Well, it looks like you go from 1 to 2, that's a 90-degree rotation. You go from 2 to 4, that's another 90-degree rotation. So it's a rotation, alright. More specifically, this would be a half turn. So from triangle 1 to 4, this would be a half turn, which is a 180-degree rotation. Alright. How about from triangle 1 to 5? Okay, so let's pick up where we left off at 4. If we pick up where we left off at 4, granted that was a half turn, but look from 4 to 5. That looks like a reflection in the line y equals negative x, right? That looks like some sort of reflection in a line of symmetry. So in the end, it's ultimately going to come down to a reflection. You're going to go with the end result. This would be, you could say a reflection, you could say a rotation reflection, but ultimately it ends up being a reflection. Yes, it's rotated and reflected, so you could put all that in there if you want to, but the ultimate end result's a reflection. Okay. Let's change this up a bit. What if we went from triangle 2 to triangle 4? So we need to figure out what the change is from triangle 2 to triangle 4. That clearly looks like another 90-degree rotation, right? This would just be a simple rotation to get from triangle 2 to triangle 4. Alright, now they're really going to throw this at you. How about triangle 2 to triangle 7? So let's pick up where we left off from 2 to 4, which is clearly a rotation. Well, if I go from 4 to 5, that's a reflection. So you have a rotation, a reflection, and then it looks like another rotation to get to 7, right? This would actually end up being a rotation. 2 to 7 would also be a rotation. Because it's reflected, then it's rotated. So you could say it's a rotation, reflection, what have you, but it ends in a rotation. Alright, couple more of these. What if we wanted to get from triangle 4 to triangle 6? What is the transformation from triangle 4 to triangle 6? Clearly that looks like a reflection in the y-axis, right? So that's definitely a reflection from 4 to 6 because you notice your x-coordinates would be negated. So from 4 to 6, that's clearly a reflection. If you go from 4 to 6, last one. What if we go from triangle 4 to triangle 8? Well, pick up from 4 to 6. 4 to 6 is a reflection. And then you have another reflection from 6 to 8, so you actually have a double reflection. So this is also a reflection. You've just double reflected it across the y-axis. So this is a reflection from triangle 4 to triangle 8. So that's it for the lesson on rotations. The next lesson will be the final lesson of geometry altogether. It's going to be about dilations. Then after the next lesson, we'll be on Algebra 2. So I look forward to that, and I hope everyone has a great day. Take care.